Hello and welcome to a video on amplifier dynamic range. In this video, we will be taking a look at the maximum output and input of an amplifier for this following circumstances. When we have clipping, when is it non-linear, and how do we get our input and output for the linear range, and we will be looking at all four the configurations. Okay, so first up would be the common emitter amplifier with the emitter resistor bypassed. We analyzed this amplifier in a previous video. So let's have a look at what we actually want. So the maximum output of this amplifier is determined by the current flowing through this resistor. So basically the voltage over this resistor and the voltage across that transistor. So with IC flowing, these two are both static. And when they start, the voltages start moving, that is when we have our output swing. So the two elements we're looking at is ICRC and VCE minus the saturation voltage. So we need to determine ICQ multiplied by RC and our Q point of our transistor minus the saturation of our transistor. So since we're interested in the edge of saturation, we will be using 0.3 volts over here. So we calculate it and we already have a Q point from a previous problem. And you can just plug in the values in here and you find 4.7 volts and 5.4 volts, and the minimum is 4.7. Now 4.7 is the maximum swing then without clipping. If we go 5.4, we actually do have clipping. Now clipping is when we hit the rail voltages. Okay, so this first one we determined without the loads. Okay, so R load is infinite, RS is 0. So we are working with AV0, the maximum gain. So to determine the input voltage corresponding, so at this point V in would be equal to Vs, we can just divide this minimum term by the maximum gain. And we find that we have an input of 27.6 millivolts and 31.7 millivolts. So if we insert 27.6 millivolts, we will be non-linear but on the edge of clipping. At 31.7 we will already be clipping, and with larger values both sides will start to clip. Okay, so this is basically to determine where the outputs will clip, and this is not at all for linear outputs. So that's to determine the maximum capability of the amplifier output. Okay, the next one is when we actually add the load of 4.7 kilo ohms, and now we need to work with a saturation current. So from the load line, one of the things that you had to determine was typically the saturation current. So the saturation current is the maximum current that can flow through this transistor like that, and our VCE will be at the edge of saturation, so 0.3 volts. So the maximum current that can flow here is VCC divided by RC plus RE. That is DC current. So we can determine it, and it's 1.56 milliamps. Right, and now we just do the whole rigmarole again that we did with the previous problem. Determine the new VCE and the new ICRC using the saturation current, and that's now 7.332 volts and 2.67, and we take the minimum. So at this point the minimum is dependent on the transistor, where in the previous one it was determined by ICRC. Since the load is attached, to determine the input voltage, we are going to use AV and not AV0. And we're going to divide by it, and we get 82.4 and 30 millivolts. So the one is clipping and the other one is just before clipping. And again, this is not at all linear. So this is at the edge of clipping. So the signal is recognizable, but not usable anymore as a pure sinusoid. Okay, so this will be the case for all our analysis is clipping non-linear zone, and then we're going to have a look at the linear. But before we take a look at the linear is what happens when we add RS. Now adding RS is basically just a voltage divider into the amplifier using the input impedance that we are seeing looking in. Okay, so the total gain is the loaded gain multiplied by this voltage division right here. Okay, so if we go ahead and rearrange this equation so that we have Vs and V out, because GV is V out over Vs, we can get the equation 1 over AV is 1 plus RS over Zin multiplied by V out. So the maximum that we had, which is not linear from the previous page, is 2.67. So when we plug it in here, and the input impedance for this amplifier, R pi is about 5 kilo ohms with a 1 milliampere and beta of 200 that we are using with a 2N quad 2. And the parallel of RB1 and RB2, we get to a VS of 55 millivolts. So we can apply 55 millivolts here and get a swing of, or a peak voltage of 2.67 volts over the load. Okay, but this output won't be pretty at all, but it won't be clipping, at least. Okay, so how can we adapt this to get ourselves the output and the input of this system when everything will be linear, when our input and output will be the same? Okay, no extra spectral components added due to the non-linear effect of this transistor. The answer is quite simple. We see V pi, or the delta VBE, as being small, around 10 millivolts peak. So now we just rearrange all of these equations so that V pi becomes our input. Now lucky for us, V in is equal to V pi for the bypassed emitter. Okay, so V in just become V pi, and we plug it into this equation. We know our Zin and RS, and we can find our source voltage from here on, the peak source voltage, and that's 19.4 millivolts. And if we multiply this with GV, which is our total gain from the source to the load, we get 891 millivolts peak on the output here, which is less than the 2.67, where we have clipping that can start, and it's really non-linear in this zone in between. So with this, our output will be linear and not clipping. Okay, so let's jump over into simulation and let's look at all 4 of these scenarios. Right, here I have my simulation setup with RS being close to 0 and R load being a huge value, so the loading is not a problem. Let's insert the 32 millivolts peak on the input here and see what our output result is. So we can see that we have clipping on the one side, and on the other side it's really not a pretty sight. It is not very linear. Now that is when we're using the 5.4 volts to determine our input. So we know that one side should be clipping at least. And the smaller one we determined was around 28 millivolts. So here it's recognizable as a signal, but we can see that the top and bottom is not corresponding quite well, so it's not a nice sinusoid anymore. Okay, so we definitely have a signal at a fairly large swing without any clipping. And let's have a look at when we actually add our load. So this was 4.7 kilo ohms. When this was 4.7 kilo ohms, one input we determined was 82 roughly millivolts peak. And as you can see, it's clipping on the one side, it's starting to clip on the top side, and this is approaching that 2.6 volts that we had, and we can see that our amplifier has these spikes where it is saturating. Right, so the other one we had here was 50 millivolts. 50 millivolts, oh, there is our signal back like we had it. Here close to -3, up here moving towards 1. I'd call that 1.7-ish. And we have no clipping, but it's seriously non-linear. Right, next one is adding our RS. And this is, what was it again? 3.9 kilo ohms. And our VS value was 55 millivolts. Okay, let's run this, and where is our signal? Still not pretty, but we have some division from the input, or from the source to the input, making the signal smaller. And see here, it is around about 30 millivolts that was required for our previous input as well. Okay, now when we calculate this maximum VBE, or our maximum V pi input here backwards, we determined for this to be linear, our input should be 19.4, let's just call it 19 millivolts, and let's run it. And now we can see that we have perfect sinusoids on the output, and with GV this is close to the value that we had in our calculations. Remember, the simulation and the calculator will be a bit off from one another, but this is our maximum input as a source is 19 milli, and our maximum output is just above 0.8 volts peak. Okay, so if we want our outputs to be linear, we need to take into consideration our VBE value at 10 millivolts peak. And if we're not caring about that, this can go up to 55, and it can go even more upwards from there if we don't mind the clipping and we're actually trying to drive something, and the quality of a signal doesn't really matter. If we put in 100 here, it will have clipping on one of the sides, so we can just drive this on and on and on, and there is our clipping, and we can see our maximum outputs with the load attached that we did calculate if we just drive this input really hard. Okay, so that is how we determine the ranges before we have clipping. the linear amplification from source to load, and then what is our amplifier's capability when we don't consider linearity, but we do care about the output signal actually clipping. Okay, so the input range of our common emitter amplifier with a bypassed emitter resistor is actually really small. If we take a look at this, is about 20 millivolts to have something decent. Yeah, you can go a little bit above. 10 milli is just the estimate, but you can see that it already starts to change here at the edge of a signal already. So this requires very small inputs. Okay, if you want a huge input here, you probably need to adjust this RS if you want to stay linear. But the common emitter with this bypassed has a very large gain in general. Okay, but not the best amplifier because R pi differs with temperature, etc. etc. There's a lot of other underlying issues. Okay, so let's have a look at our common emitter amplifier where we actually have a emitter resistor present that's not bypassed. Right, here is our split emitter, and we have a 150 ohm that's not bypassed and a 4.7 kilo ohm that is still there for the bias. So we do exactly the same as the previous problem. We determine our IC RC and our VCE minus V saturation. In this one, our Q point is a bit less. It was at 960 microamps, and our VCE is a tad higher at 5.84 volts. Okay, so in the calculation, this will end up at 4.512 volts. Dividing by the maximum gain, we get 188 millivolts and 231 millivolts. Now, this is considerably higher than our common emitter with the bypass. Now, let's start right here and recognize a couple of things. We know that the input impedance of this amplifier is much higher. We also know that our gain is less because we have this stabilizing resistor here. Now, this resistor is technically a feedback resistor, which will counter non-linearities. Okay, so with this emitter resistor, we also increase our input range for our amplifier. Right, so let's see by how much our amplifier gets improved. So that's why the split emitter is such an attractive amplifier, is you have a higher input range, higher input impedance, you have more control over the input impedance using your bias resistors. If this is very large, you have stability and you can choose your gain. Okay, so the common emitter split emitter is actually one of the famous amplifiers, if I can put it that way, because you have a lot of freedom with it. Right, on to the next slide. We can determine our saturation current again. It will be slightly less than the previous problem, at 0.02 milliamps, and we go through the same steps. And this time, V out maximum just before clipping ends up to be 2.531 volts, and this is our non-linear zone still. And if we divide that by our loaded gain, we get to 362 millivolts and 127 millivolts peak. So obviously this one is better, that one is clipping on the one side already. Right, so if we take this 2.531 and we add our source resistor, note increased input impedance, so our source becomes much higher, almost double from what we actually calculated in the previous stage. Okay, because the input impedance and the source nearly matches. So this becomes roughly 2 and our source will double from there on. Okay, so we have a very high input compared to our bypassed, where this was 55 millivolts. So this is what, 5 times larger? So yeah, larger input. Moving on to the next slide. If we want V pi at 10 millivolts, so this is when we want the linear amplification, we can do a couple of things. We know that Vin over Vs is this input voltage division, which take our input impedance of 14.54 kilo ohms in account, and that will give us a ratio of 0.493. We can do the same with V pi and Vin. Okay, Vin is sitting over here, and it's the same voltage sitting across those two. And we want V pi out. So V in being the input voltage and V pi being the voltage that we want, we can take R pi over R pi plus beta plus 1 RE1, which is the voltage over here, to form ourselves a divider. And this will give us a ratio of 0.142. If we multiply these two terms, V in will cancel from it, and we will have a ratio between Vs and V pi. So V pi over Vs is 0.07, and if we just turn this around and multiply V pi, we get 143 millivolts. So that is our input. That is a large input, considering that it will give linear amplification from that. And with the previous one, it was about 20 millivolts. So this is 7 times higher input than the bypassed emitter resistor. And our output from our input is 1.43 volts peak, which is still less than the area where it's non-linear and where it is clipping. Okay, so let's go into the simulation and have a look at these results. Right, here is our amplifier set up for the next test, and this must be 231 millivolts for our first test. So this is with an infinite load and a very small source resistor, and we will see that it starts to clip here on the one side, and it's not very linear or not very nice on the top. Okay, the smaller voltage of the two we calculated was 188 milli, and there is both sides not linear, but it's not clipping. Right, so you can see that this is a little bit more looking like a sinusoidal than with the bypassed emitter resistor, and that is because this is a feedback resistor, and it will actually improve our linearity greatly. So if this doesn't bother you at all as a signal, it kind of looks like a sinusoid, then there is nothing wrong with using this. The distortion in this is much less than our previous problem. Right, so what happens when we put in the load? This was 22 kilo ohms, and with 22 kilo ohms this was 362 milli. That's the one where it actually clips, and it clips on both sides. The taking this and putting in the 127 milli, it will be kind of linear again. Okay, it's still not linear, but it looks better than our previous problem. But that is a very large input that we have on this without even a source resistor present. Okay, so if we make this 15 kilo ohms, we can increase this input to 257 millivolts, run it, and we have exactly the same kind of output with a larger input, just taking RS into account. The last step is where we determined when it's actually linear, and this is with 143 millivolts right there, and you will see that there is actually an improvement on the signal quality right there. Okay, it's not as bulky on the sides anymore, and it calculates or it gets to 1.5 volts peak, where we calculated 1.43 volts peak. So yeah, so this amplifier is much more linear than the others. For higher input range, lots of degrees of freedom, and that is why this is one of my favorites typically to ask people to design. So yeah, there is the input range and output range of the split emitter. Let's have a look at the common base. Right, for the common base here we follow exactly the same steps as that we did with the common emitter with the bypassed emitter resistor. Okay, so again our IC, RC and VCEQ, we are looking for the swing over these components. Okay, so we get the same values, 4.7 volts being our minimum. Dividing by the maximum gain, we end up with 27.6 and 31.7, exactly the same as the common emitter amplifier. Okay, so up to this point, nothing has changed in the common base. Looking at the saturation, nothing has changed up to this point right here. We get 2.67 volts using the saturation current, but we have a different loaded gain for this amplifier since we have a larger load resistor. If these two were matched, the values would have been exactly the same. Okay, so our input voltage is dependent on a new AV value, and we get 49 and 18 millivolts on the input. And you can see that this is again very small input values. So the common base, remember, has a very small input impedance, and we need to use small source resistors with it. And that's going to be one of the big problems with our common base amplifier. Okay, so this one it will be clipping, this one will be non-linear but not clipping. So on to the next part is when we introduce the source resistor, and you'll note that here with our very small input impedance and our source being large, our Vs is a very small 54 millivolts to get to our 2.67 volts peak. Okay, so the only thing that changed here is input impedance versus the common emitter amplifier. Right. When we apply our linear V pi into this equation, note again that Vin and Vpi is exactly the same. These two are in parallel. It's just we don't have any inversion on the common base. So Vin and Vpi is again the same. Plugging it in here with a very small input impedance and compared large source resistor, our Vs can only be 30 millivolts. Okay, so again, only 10 millivolts may pass into the actual input of this amplifier. That will give us, with our GV, a 1.5 volt peak value. Okay, so the common base is exactly like the common emitter, with only this input impedance being much smaller. Okay, so let's go over to the simulation. Alright, here's our simulation. Neglectable source, very large load, 32 millivolts on the input, and here it will almost just start clipping, and it's very non-linear. Okay, so 35, it should clip somewhere, yeah, where it starts to flatten. So very small input here. Let's go to 28 milli, which is the second one we calculated. And now we have no clipping, but it is very non-linear. Okay, and that is because there is no feedback on the system right here. Okay, adding the load, I think that was 33 kilo ohms, and the input of 49 was the one. So this should be clipping and distorted. There we go. So clipping on the one side and very non-linear on the top. The smaller value we calculated, it was 18 milli, and now it should have no clipping, and this is a recognizable sinusoidal wave. It is still not very linear, but we can see it as a sinusoid. Okay, so this is because this is closer to 10 millivolts being inserted right here. Next one would be with a source of 50 ohms, and we calculated for the same output that this should be 54 millivolts. Let's run it. Output's the same. So if you're happy with a signal like this, you can use it as is. But if you really want it to be linear amplification, we need to adjust this voltage down to 50 millivolts, and our output will be 1.5 volts peak. And there we go, and we can see that this is a much nicer sinusoidal on the output. And there's the common base with clipping, linear and non-linear amplification. Okay, let's have a look at the common collector amplifier. Right, here is our common base. I used here one with two input bias resistors, so voltage divider bias, and we are not going to be concerned with V pi in this problem because the overall gain of this amplifier should be 1 at a maximum. So for this problem, it was determined that VCE is 5.4 volts and IEQ is 56 milliamps. So the MO is a bit the same as the previous ones. We just want to have a look at the DC points here on the input and output to determine our maximums at first. So we want to look at our VCE. It's still just VCE minus VCE saturation. So the voltage over here minus 0.3, so that would be 5.1. And then the total drop across our emitter resistor with this very large current that we're having, and that is 4.6 volts. So again, only the minimum of the two will do, and that is 4.6. Again, this is when we have no load. So we're going to test this later with an input of 4.6 and a bit higher to see what the effect is on the output. Right. So the maximum output that we can have is 4.6 volts. Next, we want to have a look here at the base voltage. Okay, so that is our VE value plus VBE. This is 4.6 plus 0.7. That will give us 5.3 volts. And that is from here measured to down there. And we also want the range here on the input, and that would be VCC minus VB. So that's 5.3 and 4.7 volts, and the smallest of the two is 4.7. Now, taking in mind that our input and our output will follow one another, we can have an output that is larger than the input here. Okay, so technically we need to have a look at which value is the minimum between the minimum input and output that we determined, because they must be approximately the same due to our AV0 being 1, and that would be our 4.6 volts. So you look at the DC point here, you look at the DC point here, and with an infinite load, that's going to be our maximum output before things start to clip or go sideways. Right. On to the next step. We need to find our saturation current. Now here it's VCC minus VCE sat over our emitter resistor, and that's 118 milliamperes. Then this must include the load, so we take RL prime, which is the two in parallel, it's 53 ohms, and we determine our VE point using our IC sat and our R load, and that is 6.256 volts. Then we can determine our VCE value, and that is VCC minus VE at 3.744 volts. And we still need to subtract the 0.3 for the saturation of the BJT, and that will end us with a value between this 6.25 or this one subtract the 0.3, and it will be the one subtracting the 0.3 at 3.44 volts. So our maximum output is 3.44 volts. Now we need to have a look at our VB. So our VB is just our VE value, and that must be a plus, I apologize. VE plus our VBE value at 6.956 volts. Luckily the math was done correctly on my calculator. And we need to take VCC and subtract our VB, and that's 3 volts. So between the 3.44, this must be V in. Oh, this page is full of errors. Sorry. Between our 3.44 and our 3 volts will win, and that is our output right there, as a maximum should be 3 volts and our input should be 3 volts. Now, a couple of things to note. The design equation for the common collector, is to take the peak output divided by the R load prime, and that works out at 3 volts. So that's where the design equation comes from. And always try to keep your VCE and ICRE or IERE as VCC over 2 so that everything is nice in the middle. Okay, so this can go closer to 5 volts in a real nice real world problem. Okay, so here the maximum in and out will be 3 volts, and we'll have a look at when we boost this a little bit and go up, and we will see the clipping. Okay, next step is to add the source resistor. So for that we need to determine the input impedance, that is 250 ohms. Apply our nice equation using AV again, and we will get a Vs of 7 volts with this larger resistor here, and then our output will be 3 volts. Our GV here is 0.427 volts per volts. Okay, so that is how we deal with our input, and GV is attenuation with our common collector amplifier. Okay, so let's go over to the simulation and give all of these values a try. Right, here is our amplifier set up. 1 ohm, 10 kilo ohms, that's much greater than 150. And if I remember correctly, we determined this to be 4.6 volts on the input, and then our output should be duplicated exactly. So this and this is the same, should be equal to that. Okay, so 4.6 goes straight through our amplifier with no loading effects. Let's boost this a little bit. Let's run it. And you can see that it starts to deviate here a little bit from the rest. So that is when it starts to clip. Let's make this 5 volts. And boom, it clips at the bottom. Okay, so 4.6 is our maximum output and input with the load going to infinite and our source being neglected. Let's add our source. Our load is 150 ohms. See what happens if we run it now. Now it's clipping by quite a lot. And we determined that our maximum input here is 3 volts. And there we go. Our input and output is very close to one another. It is just a little bit smaller. The gain of this was what, 0.992. If we increase this 3 by a little bit, let's go to 3.3, we should see our bottom here starting to degrade a bit. Okay, so 3 is a nice estimate for our circuit. And lastly, if we add our RS of 350 ohms, we can see that our input is quite large and our output decreases due to the voltage division. And if we take this to 7 volts peak, we will have our 3 volts peak out. Right, so this side and the output is the same, and that is quite large right there. If we start to increase this, we will start to see clipping again happening, not as fast as the previous ones because we have this voltage divider. Let's make that the 8, and it will start to become extremely clear to us. Okay, so that is how we determine the input range and output range of our common collector amplifier, and that is by determining our DC points, having them at the right places, and hoping our amplifier can supply enough current if we designed it correctly. Okay, so the load in the calculation of a common collector is kind of important in the end of the day. But if this load goes up, our amplifier becomes a lot better when it can reach the limits that we determined in the first part of the problem. So a common collector is not that difficult. It's just determining the DC points and a bit of the current, and that's it. And that is dynamic ranges of our amplifiers. Thank you for watching. See you in the next video.